Okay, so good day, grade 8 max size students. For our fourth lesson, for the fourth quarter, we have here angles formed by secants and tangents. So we're not just going to talk about angles, we're also going to talk about the side measurements involving secants and tangents. So it's angles and then their sides formed by secants and tangents. As you can see here, we have here a circle, okay, and we have here two tangent lines for our specific cone here. And also for this gears, okay, so we have these points of tangencies on these circles. Okay, so we have here these points of tangencies, and also again for the cones. There's a circle, and then we have two point of tangencies or two tangent lines. Okay, so let's try to solve this fun problem. Okay, so it's a very easy problem. Flight of the bumblebee. Flight of the bumblebee. So we need to find the value of t. Okay, so given that RP, PI, PJ, and PO are all radii. Okay, so they are all radii of circle P. Okay, so how do we find the value of t? So it's very simple. So since we know that RP is equal to RI, therefore we can say that 93 minus 2t is equal to t. And let's say this distances, okay, these distances are all in centimeters. Okay, so let's say they are all in centimeters. So solving for the value of t, we have here 93 is equal to t plus 2t. So this is going to be equal to 93 is equal to 3t. And if we divide both sides by 3, therefore the value of t is going to be equal to 31. Okay, so therefore, okay, to solve for the value of RP, okay, so that's going to be 93 minus 2 times 31. So that's going to give us RP is equal to 93 minus 62. And 93 minus 62, okay, so that's simply equal to 31. Okay, so there you go. Okay, so it's also equal to 31. So therefore, we have proven that RP is equal to 31 and PI is equal to 31 centimeters. Okay, so that's the measurement of the radius. Okay, so how is this involved for our new lesson today? So you notice that we have here all of these are radii. Okay, so later you're going to find, okay, that there are segments here on a circle that do not cross the center. Okay, so we call those chords. And later, we're going to derive new formulas for the chords, the secants, and the tangents of a circle. So given below are theorems regarding chords, secants, and tangents. We have discussed the theorems about them. Okay, so let's go and jump right ahead with this theorem about secant lines. Okay, so we have here two secant lines that intersect, okay, that intersect inside of a circle. Okay, so the measurement of an angle formed by two lines, okay, or two secant lines that intersect inside of a circle is half the sum of their intercepted arcs. Okay, so we have here this arc, okay, so that's BN and it's measured by x degrees. And then we have here OR. Okay, so that's OR and it's measured in y degrees. So therefore, the measurement of this angle, angle A, the measurement of angle A is equal to 1/2 x plus y, or 1/2 the measurement of BA. Okay, so the measurement of BA plus the measurement of arc OR. Okay, so there you go. Okay, so there you go. So this is the formula for this one. Okay. And later, okay, so we're also going to use that formula. Then we have the kind of like the opposite or the inverse of that formula. Okay, so if here we added the arcs, here we're going to subtract the arcs. So this is the theorem about intercepted arcs outside of a circle. Okay, so there's only one point, okay? Okay, one point of outside of the circle, and we have here two secant lines. That's where the two secant lines originate, from the point outside of the circle. So it says here that this angle here, okay, angle A, the measurement of angle A is going to be equal 1/2 of this first of this larger arc minus the smaller arc y. Okay, so it's equal to 1/2 times quantity x minus y. So the measurement of angle A is equal to 1/2 the quantity x minus y, or the measurement of angle A can be equal to, let's say this is arc LM and it's bigger than SP. So this can be our formula for this one. 1/2 times the quantity, the measurement of arc LM minus the quantity minus the measurement of arc SP. Okay, and then let's just try to review the tangent secant power theorem. Okay, so we're just doing all the theorem first, and then later we're going to dive right into the problems. Okay, so according to the tangent secant power theorem, the square of the measure of the tangent line in a circle is equal to the length of the outer segment multiplied by the sum of the inner and outer segments. So in mathematical symbols, we have here, if we have here the tangent line again, IB, that's going to be equal to CB multiplied by the sum of CB and GC. Okay, so the inner and the outer segments. We've discussed that in the previous topic. And later, maybe we can try to apply that one. Then next, we have the secant power theorem. Okay, so for this one, guys, we have two secant lines. Okay, so to get the measurement of QH, DV, HC, and VC, okay, so first we have to multiply the outer. Okay, the outer segment, which is, okay, if we're going to start with DC, then we start with, I'm sorry, if we're going to start with CH, okay, so we have here CH, that's the outer segment multiplied by the inner. So the inner segment is QH plus the outer, which is CH, and that's going to be equal to the same pattern that we have here. Okay, so what's the outer for this line? Okay, so the outer for this line is going to be CV, okay, multiplied by the inner, okay, by the inner, which is DV plus CV. That's our formula for the secant power theorem. So there are no squares. Okay, so the square can only be found on the tangent formula. Okay, next we have the chord power theorem. Okay, so again, to recap, we have three power theorems: the tangent secant power theorem, the secant power theorem, and then next or lastly we have the chord power theorem. So we're given here, okay, so this is what we're talking about a while ago on the flight on the Bumblebee. So we have here two chords, okay, chords EL, okay, EL and FW. Okay, so they have formed four segments. Okay, so we have EU, WU, UF, and UL. Okay, so to get the formula, okay, so to solve for the value of the four segments, okay, so we're just simply going to multiply. Okay, we're just simply going to multiply AB. Okay, so we have here A and B. Okay, so it's going to be UE, okay, times UL. It's going to be equal to UF times UW, or simply AB is equal to CD, where A times B is equal to C times D. And lastly, we have here a proof for the chord power theorem. Okay, so how can we prove this given theorem? Okay, so we're given here circle Q. Okay, so this is the center point. Okay, circle Q with chords AB, okay, AB and then CD, intersecting at point P at this point. Okay, so we have to prove that this line segment AP, okay, AP times, okay, AP times BP is equal to DP, I'm sorry, is equal to CP times DP, or simply A times B is equal to C times D. Okay, so the proof for this one, on the figure on the right, draw chords A, B, and CD. Consider the four angles. Okay, it can be said that angle A, okay, so we have here the four angles. Angle A is congruent to angle D, and angle C is congruent to angle B, since they are inscribed angles. Okay, so angle A, okay, so this one, so they are inscribed angles. They are both angle A, this one, and angle D can be found on this arc right here, on arc CB, okay, on this one. Okay, so it can be found on this arc. Okay, same goes with C. Okay, so angle C and angle B, they can be found on this arc. okay, on this big arc right here, so arc AD. So therefore, they are congruent. Angle A is congruent to angle D, and angle C is congruent to angle B because they are the inscribed angles of a intercepted arc. Because, yeah, there you go. And each pair of angles intercept an arc. So thus, triangle APC is similar to triangle DPB using the AA or the angle-angle triangle similarity postulate. So how does that happen? Okay, so we have here one congruent angle and then another congruent angle. Okay, so therefore we have here two congruent angle. So therefore, we can use the AA or the angle-angle triangle similarity postulate. So this is just similarity. Thus, the lengths of the corresponding sides of similar triangles are proportional to each other. Okay, because as we've mentioned on our previous lessons about similarity, when two triangles are similar, then their sides, okay, the length of their sides, the length of their corresponding sides precisely what they call this are proportional. Okay, so there you go. So therefore AP is proportional to, okay, is proportional to PB, and CP is proportional to, okay, PD, or A times B is equal to, okay, or A times B is equal to C times D. Okay, or we can write that as, okay, we can write that as AP. Okay, so they are proportional or directly proportional. AP times PB or BP will be equal to CP times PD. There you go. Okay, so we have all of the theorems that we need for our word problems. Okay, so let's try to solve some word problems.